Okay, so thank you very much for coming to visit us, Professor Lubin of UC Davis. And thank you very much for talking about cluster formation and galaxy formation, or else.
Okay, well, thank you. Yeah, it was sadly reminded to me that I've been doing this survey for more than a decade, which is true. So this is our survey to really study the large scale environments around a sample of known clusters at redshifts of 0.6 to about 1.3. And so this is just part of the team. So as all good professors know, it's your students and postdocs who do most of the work. So I just like to highlight Brian Lameau, who's up there in the front, who was my graduate student and is now a researcher at UC Davis, and my former graduate student who graduated last year, Lu Shen, who's there in the back. So clusters of galaxies, so we know they're quite important, and of course they're big, so they form in the densest regions of the universe. They're the most massive relaxed systems that we know in the universe. And here's a wonderful example, Abell 1689. And of course, clusters themselves cluster together into superclusters and larger scale structure. So they trace this large scale structure of the universe, which is nicely represented from the Sloan Digital Sky Survey. As a result, of course, they are very sensitive to certain cosmological parameters like the matter density of the universe and sigma 8. And with clusters, you have hundreds of thousands of galaxies at the same redshift, at the same distance from you. So they're really an ideal laboratory of studying these large populations of galaxies, albeit in these overdense regions. And we'll see that we're now able to detect clusters or proto-clusters up to redshifts approaching 5. And because of this, we can not only study how clusters form, but how this formation affects galaxies over time in these regions. So just about a review of galaxy properties at lower redshifts. So the simplest view comes from this color magnitude diagram. So hopefully everyone can see my cursor. So just color here versus magnitude. And essentially they're split into two types of populations. So bimodal. So this red sequence, which contains quiescent early type galaxies, so spheroidal galaxies, and this larger blue cloud of bluer galaxies, which are star forming and late type galaxies. So when I started the project, we used color magnitude diagrams largely. Of course, now we've gone to fancier color space, a rest frame color space. So this is an NUV R minus J diagram, which most everybody uses now. Which shows the same type of population. So quiescent up here, so they had past star formation, and this sort of blue star forming galaxies here. So unobscured star formation and sort of dusty star forming galaxies up here that tend to be redder. Okay, so a little bit about the observed evolution, and a lot of the studies on observed evolution have been, of course, in field environments. So this is work done by my former postdoc, Adam Tomczak, when he was a graduate student, using ZForge, which was a field survey using photometric redshifts, looking at the evolution of these classics, the stellar mass function and the star formation rate, stellar mass function relation. So in the top panel is the evolution of stellar mass function with redshift increasing this way. And so what we see over time is that the number of quiescent galaxies is strongly increasing with time. And the stellar mass, or the mass in stars, also increases with time. So this is easily seen as there are very strong changes in the quiescent stellar mass function. Similarly, for the star formation rate M-star relation, redshift in this case increasing up, we know that in the past, of course, star formation was higher, and so it's decreasing with time. And for a given stellar mass, you have a lower star formation rate. So that's what's shown here. So this we've also can be demonstrated both in the star formation rate density, very famous Medal plot, star formation rate density versus redshift, that we know things were much more active in the past. This results in a decrease in the star formation rate at a given stellar mass with time. while we're increasing stellar mass on this red sequence and also increasing the number of these luminous massive galaxies. So you saw that in the previous diagrams. In addition, we also know this star formation rate increase is also mirrored by nuclear activity, active galactic nuclei, right? And this is an emissivity plot versus redshift. So we also know that this kind of activity decreases with time, this black hole activity in the centers of galaxies. Okay, so when we think about clusters, we think, of course, about very dense regions of the universe. We also think about the fact that it has this very dense intra-cluster medium. And so it's generally been thought that the dense environments of the cluster core, at least, was not conducive to star formation, meaning this interaction with this gaseous medium will strip out the gas, which could in principle be used for stars. It'll strip that out and prevent the star formation. So we certainly know cluster cores, certainly in clusters today, you have very little star formation. But even in clusters today, we see, this is the effect of ram pressure stripping. The nice example here, that was coma. And this is a small group of galaxies falling into coma. And you can see the X-ray contours, which are which indicate this sort of ram pressure stripping effect where the gas comes out the back. But already with Sloan and other local surveys of local clusters of galaxies, it was clear that it wasn't just the centers, like, you know, half a megaparsec or 3/4 of megaparsec regions where you had reduced star formation. But when we look at the star formation rate, again, this is all local clusters, or relatively nearby clusters, the star formation rate versus clusterocentric distance, you still see, even at a virial radius, which is pretty far away, you still see a reduced star formation rate relative to the field. And so for many years, we studied this, like that you still have things reducing star formation and reducing the gas content, even at larger distances from the cluster center. And that's referred to as pre-processing. So if something's happening to the galaxy before it actually gets to the cluster center itself. So there are different processes expected depending on where you are relative to that cluster center. And that was a nice paper here by Moran in 2007. Okay, so this is only just to suggest that, you know, it's not just cluster cores that are important, but we need to go to other, to larger scales to see these other processes which might be going on, like AGN feedback or harassment, starvation, mergers, things like that. So going to larger scales, let's say many megaparsecs, as well as going to higher redshifts, we're going to see this kind of activity. And at higher redshift, we expect to see increased activity because the clusters are still forming. There's we expect a lot of structure around the clusters themselves because clusters together. And we also see a lot of structure in the cluster distributions of galaxies themselves, so referred to as substructure. So, and that's kind of, you can see here from the Millennium simulation of the cluster itself. And what we know is that at high redshift, the stuff, the gas, the dark matter, which is part of the cluster, will eventually be in the cluster core at redshift 0, is spread out over much larger scales at redshift 1. So this is a simulation by Simon White. So on the right is the redshift 1 picture of these clusters, and on the left is what it would look like at redshift 0. So you can see it's a lot more messy, it's a lot more clumpy, and it covers a larger scale. So for that reason was the motivation for this survey, as I said, more than almost 2 decades ago, sadly. And it was really to look at large scales around a sample of known clusters of galaxies. So the survey covered 18 clusters previously detected, either in X-ray or the optical, all at redshifts between 6 and 1.3. And the key was to go for large areas around the survey. And the design was not a single field, but was a smaller fields, obviously centered on each of these 18 clusters. But ORELSE actually covers something like the same size as some of these Cosmos and Aegis. It's equivalent in overall size to these surveys. So it took a long time just to get all the data. So we have deep wide field imaging, half a degree, going from all the B band all the way to the 4.5 micron band from Spitzer, Iraq. So a lot of telescopes were used. I think the key here for this survey was really the large amount of spectroscopy done at Keck with DEIMOS. And we did equivalent multi-wavelength studies of not all, but most of the sample in X-ray using Chandra, radio at the VLA, and the mid-infrared using Spitzer and Herschel. So this is the final results from the survey, just in numbers. So number of galaxies, so just a histogram of number of galaxies versus spectroscopic redshift. So the DEIMOS data, that's the total survey at the top, and just the confirmed members of these large scale structures of the 18 original clusters. So we have about 9,000 in total extragalactic objects, many, many more other things, stars and other things. And that's about a quarter of the size of Deep 2, which was when I was doing ORELSE, was the sort of equivalent field survey. So it's reasonably large as far as spectroscopic samples go. And we have about 2,600 large scale structure members. So it really covers quite a large variety of redshift and structure types. So our velocity dispersions range from sort of group size here, 200 to 300 kilometers per second, all the way up to very massive clusters at 1,000 kilometers per second. So this is the dynamical mass measures, again, group scale, about 10 to the 13, up to about 10 to the 15 solar masses. And quite a bit of variation, and that was the result of the selection. So X-ray selection tend to give us more sort of relaxed structures, whereas some of the optical detected clusters tend to be more messy, more substructure, some double mergers, and some really super clusters containing, 5, 6, 7 components associated with it. So because we have the multi-band, multi-wavelength imaging, we were able to measure accurate photometric redshifts and the properties associated with spectral energy distribution fitting. So this is just an example. This was work done by Adam Tomczak, was to do our photometric redshifts. And so these are this is one of our better fits, obviously. So these are the different bands. This is the SED fitting to that photometry. And this is our overall relationship between photometric redshift and spectroscopic redshift. So as we've done a pretty nice job, which on average our sort of errors here in the photometric redshifts are only about 0.03 with an outlier fraction that's less than 10%. So this provides us, obviously we have a lot of spectroscopy, we have a lot more photometry. So we have a much larger population of galaxies that don't have spectra. So our accurate photos, these really allow us to do statistical studies of galaxies. So this is that color magnitude diagram I showed you in the beginning again. So NUVR minus R minus J. This is the photometric redshifts, which have photometric redshifts cut on this 0.55 to 1.4. And you can see here, the binning here, the colors show you how many galaxies per bin. And you can see that relative to our spectroscopic objects here, that the sampling of course is not complete in this phase space, but sort of way the original selection went was that we're top heavy here a little bit on the quiescent galaxy population. And that was, again, this is over more than a decade that we started out and sort of didn't have all the information to do the targeting. So it actually got better as we moved along. So the key here is we want to be able to make sure that our spectroscopic sample, when we use it on its own, is representative of the parent sample. And so we've done, in all our papers, you'll see that we've done quite a few tests on how to convince ourselves that the spectroscopic sample is representative of this parent sample. And we find that it's not overall color and stellar mass space. So here's a very similar plot, but this is color on the y-axis and stellar mass here. And so it's this region here is where we're pretty confident that the spectroscopic sample is broadly representative of the parent sample. So most of the time we're making cuts at stellar galaxy stellar masses above 10 to the 10 and colors that are redder than NUV minus R of 2. So bluer things were just really incomplete down here. So that's good. So the other thing over the years we've refined is how we measure environment. So the goal of the survey was to see how galaxy properties change as a function of quote unquote environment. And when we started, how we measured environment, both sort of local environment, like where you're like I'm in my room, this is my local environment, but what's my global environment, Davis maybe, to tell the difference between sort of my immediate environment and sort of what we refer to as a global environment or my time averaged environment, where have I typically spent my time. And so for that first measure, we want a measurement of local overdensity. So how many galaxies are near me? Am I living in a region of space that has a lot more people than other regions? And for this, we use a Voronoi Monte Carlo technique, which is nice because it uses all the information we have. It combines our spectroscopic redshifts, which are true, so we know where those galaxies are relative to us, the photometric redshifts as well, even though there's some uncertainty, obviously, in those photometric redshifts. So this is a sample of a Voronoi method in our 1604 field. And you can see actually 1604 is a supercluster. There are 7 groups and clusters. So you can see one up here. This is just part of that field. And here's one of the clusters down there. So the advantage of this density field estimator over others is that it's scale independent. It can span a wide range of physical lengths. And maybe most importantly, we don't make any assumption on how your cluster looks. It doesn't have to be round to pick it up. And so this is really important, especially where we see a lot of clusters are not relaxed at this redshift. So the way this works is you have a field and you select a redshift slice, which has a certain width shown there. You use your spectroscopic redshifts if they fall into that redshift slice, and then you Monte Carlo the photometric redshifts using their individual errors, meaning you put galaxies in this redshift slice if its photometric redshift tells you it should be in that slice. And the Monte Carlo is because, of course, there's some error in that photometric redshift. So we calculate the Voronoi region in each iteration, and then you sample a grid just to make it easy. And then you reiterate that 100 times. So you resample the photo Z's and create a new density field. And then you median combine that to get your final density field. And from that, we define an overdensity. So overdensity, meaning it's relative to the mean density of this field, which is nice because you need to eliminate any variation from field to field if you're going to compare every field together. And so then you just step to the next bin, and these bins do overlap, and then you step to the next bin. And so there's a nice little movie which shows that for the field of RxJ 1053, and Jillian may remember that number. So it's starting out at 0.55, so not much yet.
I remember it well, Lori.
I know. So it's really old school. It's really dating me. So that's 1050. That's RX 1053 coming up at redshift 1.1 as this, clear overdensity. It's also a merging system. This is something at slightly higher redshift. And you'll see we pick up things that we didn't necessarily mean to target. This is at 1.3. That is a new detection in our survey. So that's how that, so we can, using these density maps, not only can we study the density field in the original clusters and the original large scale structures, but you can find other clusters this way as well in the same field. Okay, so the second technique would be this eta parameter, which I know Jillian and Go Green have also used very extensively, which is the sort of time, gives you sort of time averaged density field that your galaxy has experienced. This is more traditional, meaning you're going back to, say, clusterocentric distance or something like that, but it uses both the projected radius as well as the sort of velocity. So the global environment here is only for spectroscopic data, obviously. And so you can split it into this sort of phase space here, which is relative velocity relative to the velocity dispersion of the cluster versus this projected radius relative to R200. And these regions sort of delineate different types of things. So close to the center, this sort of, not like a cone, or I forget what they call it, but sort of at eta less than 0.1, you're considered in the virialized core region. As we move further out, it's more of an intermediate region where maybe you have galaxies first coming in, but maybe also galaxies that are backsplash galaxies, so they've made already a pass. Then you have the sort of traditional infall region further away. Out here, which is recently accreted galaxies, and then you have regions where it's unlikely that it's associated with the group or cluster. So this is the global. Eta is our global measurement, and log 1 plus delta gal is our local overdensity measure. Okay, so with that, we can now look. The purpose is really to study how galaxies vary depending on redshift, environment, and stellar mass effects. And so this is our histogram of all our data. Again, just number of galaxies versus redshifts, again, split into quiescent versus star forming here using that color space. This is the region in overdensity space we cover. So we actually go from sort of field environments, is the nature of our technique, all the way up to these sort of very, very dense regions up here, which are not, are not covered in anything but a cluster survey, obviously. So field surveys, you'll see, when I talk about Cosmos a little bit later, never reach this kind of overdensities. And then, of course, we also get reasonably high mass galaxies all the way up to greater than 11.5, 10 to the 11.5 solar masses. Okay, so every time I try to give this talk, this is just some of the stuff we've done in ORELSE, which is now published. So I'm not going to talk about everything. It's some I can't even explain really to an audience. It's too complicated, even for me. Sometimes my students figure. So I'm going to pick a couple things which just highlight the data itself, like what we have to work with in case people are interested in using our data. So the first thing is the full cluster catalog. So I mentioned that we had the original clusters that we targeted, 18. Then we had found other groups and clusters associated with those 18 in the large scale structure. So that's about 55. And now we can also look for other detections in the field using that, stepping through those redshift slices in our density maps. So to create really a full cluster catalog that the others are not spectroscopically confirmed, but they're overdensities in our maps. And so this was really nice work done by Denise Hung, who's a graduate student at the IFA, working with my former postdoc, Roy Gao. And so she used these density maps and ran SExtractor, which is just an image detection software on these overdensity maps to automatically detect group and cluster candidates. These will also should obviously detect the known groups and clusters as well. And so the parameters used for the detection were optimized using the confirmed group and clusters, the ones we knew were real. And so because it's an automated technique, we've been able to estimate completeness and contamination using the mock galaxy catalogs. And so we have now a sample of over 400 new detected clusters in this survey. And so this is a nice figure which shows you sort of the linking through in SExtractor through these redshift slices. So a detection of a cluster will appear in multiple redshift slices, but the sort of flux, the isophotal flux from SExtractor is going to peak in one of those slices, one of those redshift slices. So the peak of that isophotal flux will give you the actual estimated redshift of the cluster, and the integration of this sort of Gaussian will give you the total sort of intensity or flux from the cluster itself. So this is really nice. And so this total integrated flux, we want to calibrate that so we can estimate a mass, right? Because the whole thing is you want to know the mass of the group or cluster. And so we use the spectroscopically confirmed groups and clusters, their total isophotal fluxes, their integrated fluxes, where we have measured virial masses, and we do a fit. So this fit is used to calibrate the total mass of our candidate clusters of groups and clusters of galaxies. And you can see, we're not, below 10 to 13.5, 10 to 13.5. There's a lot of scatter here, and we're not super complete at the sort of group scale whatsoever. And she just finished a nice work which used this to measure the cluster mass function at redshift 1, which you see there. So this is the cumulative mass function as a function of cluster mass. And we can compare that then to theoretical mass functions to try to constrain these two parameters, sigma 8 and the matter density of the universe. So this plot just shows you for fixing sigma 8 here at 0.8, which is a canonical value, and fixing sigma omega matter here at 0.27 and varying the other parameter. So we did, in fact, come with a measure of cosmology from clusters at redshift 1. And when I started ORELSE, I said, we'll never do cosmology with this survey because clusters are too weird. And yet here we are. So I'm pretty pleased with this, even though we get, we're consistent within the large errors, of course, but we do get a high sigma 8. So we get a sigma 8, which is significantly higher than the canonical value there from Planck. Even removing the known clusters and calculating the best fit parameters, you still get a high value. And this may well be due to the fact of the selection of this survey is that we are really targeting special regions of the universe, overdense regions, and this may bias our results in this kind of thing. But it's really just a proof of concept that this certainly can be done with this kind of cluster survey at redshift 1. And I know your students already working on this for Go Green. Okay, so the main thrust was really to study environment. So here are some of those results, how environment affects galaxies. So this is, again, work done by Adam Tomczak. This is the stellar mass function, now plotted as a function of local overdensity, regions of different levels of local overdensity. So local overdensity is increasing upward. So this is our highest density region. So this is this is at roughly a median redshift of about 0.9. So in the highest density region, you can see it looks very, very different from the lowest density region. And the sort of shaded here is from the field survey from Z-Forge. So the lowest density regions of our survey are consistent with the field stellar mass function at this redshift. So you can see a very strong change with density is that you're increasing highly the number of high mass galaxies and you're sort of getting rid of getting rid of the lower mass N. So Adam, so how can we go from, say, some field stellar mass function to a stellar mass function in high density regions, which looks very different? And for this work, Adam did a semi-empirical toy model to see if merging of galaxies in that field stellar mass function could explain the resulting stellar mass function in the highest density bins. So this is the model here, which shows the stellar mass function, and the color coding here is for different fractions of merged galaxies. So the one at the bottom, the resulting stellar mass function at the bottom is for 95% of galaxies merged compared to 0. And the toy model starts out at a redshift of 5 with the stellar mass function as measured at redshift 5 so far. And so it includes all this stuff. Galaxies are going to grow via star formation. They're going to quench. They're going to merge. And he uses prescriptions from the stellar mass function star formation rate relationship, the quiescent fraction, stellar mass relationship, and merger rates, and how these change with redshift. And so there's minor mergers, there's major mergers, and some of the mass in these galaxies will be converted into the interstellar light, like 30% or so. And these are, again, it's a toy model, it's just to see if it works. So here are the 3 top bins. And if I go back quickly, you can see there's a very strong change between the 2 lowest density bins and the highest density bins. And even in sort of this intermediate density bin, you already see a strong merger fraction based on this toy model. So 79% of galaxies have experienced mergers, even in the intermediate density regions. And that climbs to about 89% in the highest density regions. But the biggest change is from the low density to this region there. So this really suggests that this rapid increase really means that, in these intermediate densities where you would probably expect galaxy mergers to occur, you are seeing them happening. And so it's very important. Galaxies are at least very important, maybe not totally important, but very important in shaping the stellar mass function in high density regions. So that's his. So keep in mind, this was using only photometric redshift, so it's a statistical study because we needed the large samples. But this is one of the nice ways, and Adam also did a study of the star formation rate stellar mass function and how that changes with density as well using a similar technique. So that's that. The nice thing is we do have galaxy kinematics. So in addition to redshifts, the spectra, we chose to take spectra at very high spectral resolution, so R5000 with DEIMOS. So in some cases, we are able to measure rotation curves for disk galaxies. And here are some 4 examples of the O2 lines observed, right, where you can see the rotation curves clearly. Here are the galaxies with the slits and their PAs. And so this is work done also by a former postdoc, Deborah Policia, who originally had done such a similar analysis in Cosmos, in disk galaxies in Cosmos at the same redshift at 0.9. And she did an equivalent study here in ORELSE, one of our ORELSE targets at redshift 0.9. And so you can see this is the data, this is the 2D spectrum, this is the model, and this is the residual, and this is the resulting rotation curve. So the first thing you do with rotation curves, of course, is measure the Tully-Fisher relationship. And so Tully-Fisher, for those, Tully-Fisher is a little old school, but is absolute B-band magnitude, so luminosity versus rotational velocity. So as I said, Deborah, for her thesis, actually did this study with Cosmos, HR Cosmos, also to redshift 0.9, but Cosmos is really largely a field survey, and so doesn't cover the high density regions that our fields do. And you can sort of see that here. Here's the number of galaxies versus this log 1 plus delta gal or overdensity. So this is HR Cosmos here, shown here in green, and this is the 1604 field at redshift 0.9. So you can see we extend much farther to higher densities than Cosmos. So it's really a relative field to a high density region comparison. So Cosmos is lower densities, but it's also brighter magnitudes. Our survey goes fainter than the Cosmos spectroscopic survey. But right away, you can sort of see that the Cosmos data here in green sort of follows the same relationship as the ORELSE. So there was no obvious change in the Tully-Fisher relationship, which compares luminosity to rotational velocity. But where we did see changes was in the stellar to dynamical mass ratio of the galaxy. So of course, you can use rotational velocities and an estimate of the galaxy size to measure the dynamical mass. And when compared, so if you do the stellar to dynamical mass ratio, the ORELSE field here shown at the top was systematically higher. So it's a higher stellar to dynamical mass ratio. And that was a statistically significant result. And this was not due to the rotational velocity, it was rather due to the smaller size, this R2.2, which is related to the scale length of the disk, a smaller size of these galaxies. So it appears the galaxies in denser regions are on average more truncated than field galaxies. And this is they're based on simulations and other things. It's known that some environmental processes such as merging or ram pressure stripping can actually make the size of the galaxy smaller. So this is confirmed here using this analysis. So these are two examples of how we've used environment in different ways to measure different galaxy properties. The other aspect of the survey was this ancillary multi-wavelength stuff, in that we wanted to study the active galaxy population. So everyone knows the universe is more active in the past, and that involves star formation and also nuclear activity. So we had Chandra data on most of these systems, or they already had Chandra data. And we looked at X-ray detected cluster members, and again, used the properties of their host to try to understand what was going on. So this plot here, these are 61 X-ray detected large-scale structure members, so they are not necessarily in the core of the cluster. And this is their X-ray luminosity as a function of essentially color or red sequence offset. So if I go back to our color magnitude diagram, right, there was this sort of blue cloud, so things which are really blue. There's galaxies which fall in this red sequence here, so very red and quiescent, so no star forming. And then, I don't know, Jillian, I think maybe the Green Valley has lost its oomph. I haven't heard from it in maybe many years, but there was a lot of discussion about Green Valley galaxies at one point, which is like a transition. So they're blue galaxies that used to be, obviously, they were blue galaxies. At some point, you've cut off the star formation or remove the gas or used up the gas, and they're going to transition to the red sequence, and they're going to spend some time, not a lot, in this transition, so in this Green Valley, as they're aging, as the stars age and the more massive stars die off. Jillian, yeah, it's old school, right, Jillian?
No, I disagree. Green Valley, really? Green Valley is alive and well.
Is it?
We're just doing it in 2 or more dimensions now.
Okay, I don't know. Yeah, I haven't heard
X-ray UVJ, there's still a Green Valley, but we have to correct for dust.
Okay,
I would say. Well,
I just haven't heard it said in a while. Sorry. So it's just an aside. Okay. Well, that's good to hear, because the green, you don't want to skimp on the Green Valley galaxies. So you can see we cover sort of these most X-ray luminous hosts are blue galaxies. And so we can use our spectra, the composite spectra, to sort of estimate sort of the ages of these galaxies. So age meaning the time since the last major episode of star formation. And so in the composite spectrum, we did this using the strength of H delta and D4000 and comparing them to Bourgeois and Charlot models. And so region 1 here, which are high X-ray luminosity blue galaxies, are quite young. So they're consistent with having a coeval nuclear activity and its starburst or star formation activity. And as we move to the Green Valley, we see a mix of luminosities, but they're all older. So they all have, their composite spectrum is an older stellar population. So ages maybe a half a gigayear or so. And maybe even more starkly, all red sequence hosts, X-ray hosts, are much older, so several gigayears, and they're all low luminosity. So you don't see anything in this region. A red host does not host a very luminous X-ray AGN. But this whole picture says that we really have this a relationship between AGN activity and current star formation. So there's some common origin to this sort of level of activity. And so to bring it back to environment, so this is again global environment, so our eta parameter, we can look at AGN hosts relative to the overall population of regular galaxies. So AGN, so this is our phase space again, X-ray detected members shown in red. And so there's no obvious global environment for these galaxies. They follow sort of the same distribution of all other galaxies. So this suggests that the triggering mechanism of this X-ray nuclear cavity, at least, is not really dominated by the global environment itself. Ooh, go back. Okay, so this is work done by my former graduate, Lu Shen, who has taken over all of our radio work. And so obviously like X-ray emission, that's certainly due to AGN, but radio emission can be due both to AGN or star-forming galaxies. And so there are three types of radioactive galaxies. We talked about the AGN, the star-forming galaxies, and what is referred to as this hybrid population, which is sort of intermediate between star formation dominated and AGN dominated, and it has a very high accretion efficiency. So using the radio data, of course, you want a way to classify the difference between these three different types. So the first thing we do is we do a maximum likelihood matching to the optical image, to our optical data to get its host. And then there's a two-phase radio classification, one being the intensity, the luminosity. So very luminous radio sources above 10 to the 23.8 are likely AGN, because you can't, star-forming galaxies can't produce such a powerful radio emission. Below that, you're likely to have some sort of mix of AGN and star-forming galaxies. And then there's this color SRL technique, which is just shown here in the cartoon, which is dust-corrected color versus this ratio of radio power divided by stellar mass. So they sort of fall into three regions, sort of AGN here, hybrid here, and star-forming galaxies here. And this is calibrated using QTIR, which is a ratio of the total infrared luminosity to the radio luminosity. So a galaxy which has a lot more infrared emission is a star-forming galaxy because you have reprocessed dust. And things that where you have a low QTIR, that's going to be at AGN, and hybrids will be somewhere in between. So this was calibrated using only those data that where we had total infrared luminosity, where we had the Spitzer or Herschel data. So that's not the entire, so the MIPS data from Spitzer or Herschel data from Spire. So that's not the entire sample, is not covered by the infrared data. Okay, so that's the classification. And here are some of her results. So as you might expect, we see large differences in the properties of the AGN. So these are all cluster. These are all large scale structure members. So here is a composite spectrum showing the three different types, AGN, hybrid, and star-forming galaxies. So the radio AGN, as you might expect, are tend to be old stellar populations. So this is a plot versus dust extinction versus, again, age of the star, which is when the last major episode occurred. So this is using a spectral photometric fit, using both spectral data, composite spectral data, and photometric data. And so the AGN are less dusty, but they're also significantly older, so they fall here. In comparison to star-forming galaxies, which have some emission, obviously have some emission lines, they tend to be more highly extincted and tend to be and are the youngest. And the hybrid is somewhere in between. So they're sort of younger, but not the youngest, but they have the strongest emission. So they have, so this is due to this high excitation emission lines due to this sort of AGN component. And so the hybrid is not, they're a different class from the AGN and star-forming galaxies. They're not just a mix of the two because they have this these strong emission lines associated with them. So again, the goal of ORELSE is environment. So we see they're different environments. So AGN tend to really populate the core, the central regions of clusters, whereas star-forming galaxies tend to be in this intermediate region, and hybrid galaxies maybe slightly tend to be further out. So the question always with these special galaxy classes, like X-ray emitters or radio emitters, are the differences we see in the environment due to the fact that they're radio emitters, or they just due to the fact that radio AGN tend to be more massive, and those tend to be in the centers of clusters more, or whatever. So you want to be able to distinguish between whether it's the radio emission makes them special or something else is making them special. And that's one of the nice things we can do with ORELSE is the control sample. So what we can do is look at galaxies that have the same properties in stellar mass, color, and redshift space as the sort of, let's say, radio AGN. And we can have a control sample to see where do we find these types of galaxies that are similar in all of their properties to our radio AGN. And then you can see, are the trends we see in environment really due to the fact they're radio AGN, or are they due to the fact that they're just a special population of the overall population? And so we can use that to really determine if the trends we see with the environment are really due to the fact they're special galaxies. And you can sort of see that here. This is a cumulative distribution as a function of this eta parameter, our global parameter, going from the cluster center here to infall regions. And we do see that there's significant differences in the AGN population. You see they tend to have more galaxies in the center, and also for star-forming galaxies. So these two distributions are not the same, whereas for hybrid galaxies, there's not a strong difference with the control sample there. So there's no significant detection on this sort of environment there. Okay, so those are sort of how we're using the multi-wavelength stuff to study active galaxies. And as I said, there's a lot other things we've already done, but there's a lot more that can be done with ORELSE if people are interested. So I'm just going to use my last bit of time here to discuss our next phase. So I kind of like to say ORELSE is dead, but it's not really. But we're actually kind of bootstrapping off ORELSE to do something a little different and to go further back in time. So this is our new survey, which is called Charting Cluster Construction with ORELSE and VUDS, or C3VO. Took me a while to fit that into the name, but we got it. And so this is combining ORELSE and everything that's in it with a higher redshift survey, the VUDS, the VMOS Ultra Deep Survey. So VUDS was done by Olivier Lefebvre at LAM in Marseille. So he has pioneered these very large redshift surveys, of which VUDS was one, and Vipers, and there are many other surveys. And this one was targeted, a very deep survey, a smaller area, only 1 square degree, targeting galaxies specifically at redshifts of 2 to 5. And VUDS are in these very historic extragalactic fields. So they have, all the bells and whistles, all the multi-band data, all the ancillary data. So they have everything you'd ever want already. And their peak of their magnitude distribution, it's obviously fainter than ORELSE, about 2.5 times fainter. So they go to an I band of 25.3. So it's essentially the equivalent survey to ORELSE, and we can use the exact same techniques like measuring overdensity in the same way at higher redshift. So the purpose of going to higher redshift is to look at how clusters themselves form and to detect and study protoclusters. And so this is the redshift of ORELSE, and this is the redshift of the new survey. And so clusters today don't contribute a lot to the overall star formation rate density, but protoclusters are regions of enhanced activity that they're actually contributing 30% or more of the star formation rate density at redshifts of 2 to 5, even though they only contribute less than 5% of the overall volume. So again, this is our star formation rate density plot that I showed you in the beginning. And you can see today clusters don't contribute a lot of that, but here they are at redshift of 2 to 5. You see they're a much higher fraction of the overall star formation rate density. So we expect them to be incredibly active. So this is the sample. They've already detected a sample of roughly 50 spectroscopically confirmed, albeit not as many members as ORELSE, between redshift of 2 and 4.57. And so they typically have a few, between a couple to maybe 10 or so confirmed redshifts per system. So it's an equivalent number of spectroscopically confirmed protoclusters as we do have clusters and groups in the ORELSE survey. So it's a sort of nice one-to-one comparison. So this is one of maybe the most famous ones that was not detected in it because it's already known. This is a supercluster at a redshift 2.5 in the Cosmos field. So they already knew about this already. And you can see, so it has 7 different peaks. It's a very large structure. already at redshift 2.5. So that's part of it. And this is the highest redshift run at 4.57. So as part of this survey, we are also doing a Keck, DEIMOS, and MOSFIRE survey to get additional redshifts in the 5 most significant peak detections in this survey to really better constrain the distribution of galaxies. And you can see some of our, this is only after a few masks, we're not complete. So this is the original density field at 4.57, and the triangles here are the VUDS members, and here are new members, and you can see it's really changed how that density field looks like for this structure. So we expect to like triple the number, at least in these 5 detections. We can also do the similar analysis and say, look at radio and X-ray emitters. That's my dog, say hello. This is at redshift 3.2. This is in the I think this is in the XLS, the XMMLS field. It's at a redshift of 3.2. And you can see it's a very complicated structure with several peaks. The proto-BCG here was originally detected in X-rays as well as a type 1 AGN. But we recently looked at VLA data that we took in this field for another reason and found a very strong radio emitter. This one is also a radio emitter, but this is at 10 to the 16. It's a radio emission of about 10 to the 25. So it's very, very powerful and not associated with the main peak. And it's also extremely massive. So I know Jillian's interested. It's like 10 to 11.5. In stellar mass at a redshift of 3.9.
Nice.
So you could see it's right there.
Nice.
Yeah. So it's interesting that it's more massive than the main galaxy and the main structure itself, and it's very, very different. It's quite red. It's pretty quiescent as well. So this is color magnitude, color, and color stellar mass. The proto-BCG here is very, very blue. It's strongly star forming. It was also detected in Herschel at about 750 solar masses per year. So these structures all look very interesting. So we're pretty excited about the survey.
Is it in the field for any of the Lyman alpha tomography surveys by any chance?
Is it? It may well be, because these are very traditional, like everybody looks at this field. So it is very possible. And I think that's one avenue that other people were looking at with VUDS, is to study that. So the fields are Cosmos, the extended Chandra deep field souths, and the XMM. Why can't I remember the XMM or LS something, or the 3 fields?
LSS? Or...
Yes. Is that what that's? Yeah. Yeah. So the nice thing we can do, so I'm ending here in a few minutes, is that the key thing of combining so VUDS is great on its own, but the key thing is to combine VUDS with ORELSE and sort of make equivalent measurements at high and low redshift. So this is a measurement in ORELSE of the star formation rate density relationship, which shows you this the anti-correlation between star formation rate and density. This is using corrected O2. And this is the same measurement in the VUDS fields at redshift 2 to 5. So that we're only covering the smaller range of overdensity, obviously, but we can measure the same sort of properties and use sort of equivalent local overdensity measures. And already in VUDS, you see this reversal of the star formation rate density. So instead of trending down, you see that it actually, for the highest mass galaxies, is already trending up, suggesting high density regions are regions of active star formation in the past. And then finally, it's going to be this direct matching of descendants to progenitors. So using sort of the halo mass growth function and comparing how using n-body simulations like the Millennium simulation, we can use this growth of structure to compare the progenitors in VUDS directly to the ORELSE descendants, and then compare protocluster to cluster, and then compare the galaxy populations and really see how they're evolving directly with time. So that's the new survey, and I'll just leave it there and I'll turn on my light. It got dark very quickly. with all the stuff we've done recently, if you're interested in anything else, and I think more is possible, and we are willing to share. Like, we are happy to provide people with data if they have interesting things to do with it, because I think there's a lot there that I feel we've done what I wanted to, but we're welcome to have other people use it and do great things with it as well. So I'll stop there.
All right, thank you very much. That was a great talk, and I think a fitting capstone to the quarters colloquia. Who has some questions? So while everyone is thinking, I feel I'm kind of contractually obliged to ask about your sigma-8 relationship. I know you said you don't. It wasn't a serious measurement, but can you? I mean, do you have an estimate of how overdense your region is?
Well, I mean, so you saw like my original plot of like, we're really selecting on, very atypical regions of the universe, so that they're centered on known clusters of galaxies. So yeah, so they're really overdense. So it's not unexpected. I think we got a sigma-8. I think, and even the problem with even removing the known structures, which means spectroscopically confirmed structures, we still have other structures that we haven't spectroscopically confirmed, which are likely associated with those larger scale structures. So they are still in the calculation. So yeah, I think they're not typical. I mean, as I said we will never do cosmology with the survey. You'll never do cosmology with high redshift clusters, because if you look at them, they're messy. Like, how do you measure virial mass really well? They're not virialized maybe. So I think I was just pretty pleased we actually did it, rather. But I think we're definitely biased to the high end.
Okay. Gillian has a question.
Well, first of all, it was more of a comment. It was to say how impressive it is to pull together this body of work. And of course, it took years because you were doing a deep field survey on every single cluster. So you had to do multiple deep field surveys. I just wanted to say how impressive the body of work was.
Oh, thank you.
I wanted to ask you if you had anything. So a couple questions. One is about post-starbursts. You have, I know, at least one paper, several papers on post-starbursts.
Yeah.
And then the second question is, it's difficult to compare apples with apples. How are you determining the mass of your higher redshift sample in order to be able to start making that comparison?
Yeah. So what was the post-starburst question? Was there one before I get to the math?
Well, it was.
Oh, sorry.
Insights from post-starburst.
Oh,
because we have done one of those dynamical pictures with the post-starburst galaxies and found they lie in special places, and you can do some kind of timing analysis. And I wondered if you had some comments on that.
So that we did, right? So that's some of the work we did. Actually, that was maybe some of the earlier work we did.
Yeah, I'm seeing a paper from Brian
Yeah. So we did see that that post-starburst, there were differences actually between post-starburst galaxies in higher mass clusters versus groups. That it really seemed to be that a scenario of where you have infall into the cluster, then you'd have some sort of stripping thing, and those would remain stripped. So they didn't. Whereas in groups, it was this sort of possibility, and they would become sort of what Brian called kairos things, which so there's a difference between sort of traditional post-starburst galaxies, which still show the line emission, and the sort of which don't show the line emission, and then sort of this class which still show the line emission, which is likely due to AGN, and that was sort of an age difference. So they would like evolve to one to the other. And in clusters, it was clear they just evolved that. They evolved to the typical post-starburst galaxy and then to a quiescent galaxy. And that's likely due to stripping. Whereas in groups, there may be a possibility that can have rejuvenation, where you can actually not go finally to the quiescent, but you can actually gain some gas and sort of become a star-forming galaxy. So those were the kind of difference we found as a different of at least the sort of parent host of where post-starburst galaxies were.
Okay.
Yeah, we left that a little, like it was really, and then we got sidetracked with other things, but that's still all there. I mean, all that data is still there with the measurements of the O2, H delta, and we have a sample we took with MOSFIRE to look at H alpha, right? Because we were concerned that we were misclassifying post-starburst galaxies with the O2 emission. Well, not classifying real post-starburst galaxies because it had O2 emission, but they really were post-starburst galaxies. Okay, and the mass, that's a good question. Obviously, you can't use virial mass estimates when you have 5 galaxies or, and it's clearly not a virialized structure at redshift 5. So there are ways to measure using the overdensity maps. So it's like a 3D, a 2D, and a 3, or you can use a 3D measurement to use the overdensities, within some contour to estimate the total mass. And you can do the same thing for well, you have a virial mass of ORELSE, but you can do the same independent mass measurement using the overdensity mass for ORELSE structures. So if I go back, this plot here is actually is the mass from the overdensity mass versus a virial mass. Now, for each individual component, whether you believe that virial mass, and you can see actually there was a reasonable correlation even at 2.5 between those two independent mass measurements.
Yeah, it's hard. Thank you.
It's very hard. Yeah.
Okay. Any other questions?
Can I ask a question?
Oh, I have a question. Go ahead.
Right. So this may not be a well-informed question, but as you point out, the trend that you see more active star formation and higher redshift structures is very striking. Can you say, as we're looking at these protoclusters at redshift 4 and 5, what fraction of the stellar mass of lower redshift clusters do they account for? Does that make sense?
So what fraction of, maybe we could go back to this plot. So you mean of the total? So you mean stellar mass? So of the mass in the galaxies or the total mass of the cluster? Sorry.
Oh, I don't know. I'm just wondering, are we how big is the tip of the iceberg that we're seeing at redshifts 4 and 5 in terms of what ultimately, gets into these clusters?
Well, so I think when we think about sort of how this would show an example of how the sort of total mass of a redshift 5 protocluster would be. So if it's at 10 to the 14, and that's going to grow up to this point in total mass by redshift 0 on average, right? So I think there's so I think over time, of course, the protoclusters they're gonna start out less massive and they're gonna accumulate material around it. So they're certainly gonna grow. And I think the key here is that their contribution to the star formation rate density, which is of course creating the stellar mass. So I'm not sure how to answer that exactly, but of course they're producing a lot of stellar mass, whereas today you don't see that active, the sort of stellar mass you're producing now is like the clusters are not doing that anymore.
Yeah. But it's a decent fraction, I guess, in terms of halo mass as you're showing here, and it sounds like also the stellar mass. You're sort of you're really seeing the buildup.
You're really seeing the buildup, and I think these protoclusters are the really regions of enhanced star formation. So it's really you're creating these likely creating these higher mass galaxies in these overdense regions.
Yeah. Thank you.
Any other questions? Okay, well, in that case, let us thank Lori again for a wonderful talk.
No, thank you for inviting me.
Yeah, and I hope you'll come and visit us again.
I hope so too. I certainly will. I certainly will.
I hope so. All right. Bye-bye now.
Okay, thank you.
Happy holidays, everyone.
Yes, have a good break.
Bye, Lori.
Thank you, Lori.
Thank you.